Hi, everybody. It is the 8th of May. It is, in fact, let me see here, 1 month exactly after the big eclipse that was on April 8th. And it's hard to believe that so much time has gone by. And we do have a few interesting things happening in the weather, and we will talk about that in just a moment. First of all, this is the last lecture of this particular portion of AER 110. And all of the material, including all of the assignments and the test, are all due by midnight on Sunday. So make sure that you have all that done. All right, let's see what we got here. Looks like there's snow in the High Sierra and a few clouds that are developing here in the foothills. Meantime, down to the south, what is this? We have a little bit of low cloudiness. Not a lot, though, just a little. And we do have a change in the air mass. It's coming in from the north. In fact, if you look over here in Utah, right there, you can actually see some cloud streets showing the northerly direction of the wind coming down that one valley right there. And I just noticed a fire right there in the, let's zoom in here, fire in the Flagstaff area. Let's see, right there. There it is. You can see a fire and a little bit of pyrocumulus right around it there. So just couldn't help but notice that. Anyway, we'll come back to a wider view here and see what's happening. It looks like a big cyclonic zone of low pressure across Idaho, Wyoming, the northern Rockies, and out over this area here. There's been a lot of severe weather. 2 days ago, we had a high risk area in Oklahoma. Yesterday, we had actually more tornadoes in Michigan and parts of Ohio from only a moderate risk. And today, the risk is back. It's going to be a moderate risk. But let's take a look at our weather here. So here is the current look. And you can see in Bakersfield, we have 71 degrees. Along the coast, we're about the same in the 70s. All the way down to San Diego. Let's see what the temperature is down there. It's in the mid 60s, and over in Phoenix right now, 85 degrees. But you'll also notice that the winds are beginning to pick up out of the east-northeast in Sandburg, also China Lake, and over here to Edwards Air Force Base, and the dew points are much lower. Here's what it looks like if we were to just look at this. We'll always take a look at Fillmore, see what's happening there. 72 perfect degrees, and the dew point is 53. And that's very, very nice. But just over here to the east, you can see, don't even have to go all the way to the 5. And now we have easterly winds gusting to 28. The dew points in Fillmore, the dew point is 53. Over here, the dew points are in the 20s. So there's like a little front. There's a little dry front, which is coming through. And this is could be a Santa Ana situation. That would be strong northeasterly winds. Here's a location in the San Gabriel Mountains right there, Magic Mountain Truck Trail. And the winds have shifted. They've been gusting up to 49. So we're beginning to see that. This is often a potential fire situation. And it's real easy to see. You look down here, you see the temperature and the dew point. Just look at the dew points in blue. They're in the 50s throughout the Los Angeles basin here. Here's Anaheim with a 54-degree dew point. But then you come up here, and you can see the dew points are much lower in the teens, and the winds are out of the northeast. So this is going to be not a big deal, but it's going to be certainly notable. Here across eastern Kern County, dew points are in the teens. Winds are out of the northeast. Over here in the San Joaquin Valley, temperatures are in the 70s. And for the most part, the dew points are in the 40s, so they're higher, and the winds are fairly light. If we go far enough to the north and to the east, now we're talking. Okay, so here across the Nevada National Security Site, I guess that's just read Area 51, winds are out of the north at gusting to 33 in this location. The dew points are in the single numbers. So it's very, very dry. It's probably not going to last, though. And all across Utah and Nevada, generally northerly winds. Over here in the Owens Valley, it looks like the winds are beginning to pick up out of the north. Dew points are low. So what we're doing is we're analyzing the air mass. We're looking at the temperature and humidity, discontinuities, wind shifts, and stuff like that. So that's what's taking place right now. Okay. So, wonder what's going to happen. Let's look at the models. So here is the model for Bakersfield. This is the North American Mesoscale model, the NAM, as we like to call it, which is usually a pretty good. It's a little bit of an avant-garde model because sometimes it'll be a little bit out of the box with temperatures and things like that. Anyway, it says today's high about 79. Tomorrow's high in Bakersfield about 84, and then we're up to 86 the next day. The GFS, which is the global forecast system, that's the big American model. It says about the same, 79. I think it might hit 80 today. And then 88 and then 90 degrees the next day. So a warming trend with a very low humidity. And here is the big picture here going all the way out to Wednesday. It shows clear skies until the very end. Wednesday, some partly cloudy conditions there. Temperatures peak around 93 degrees on Sunday. And the National Blend of Models, let's see, I looked at that, and it is pretty much the same. It goes 80 for a high today, and then 88, and then 89. Let's see what we have here. Let's take a look at the big picture. We're going to go out. Wait a minute. I want to look at this and see what it said. Temperatures go down. Okay. So let's take a look at the extended for not only Bakersfield, but our good friends in Oxnard, our good friends in San Diego, and our really good friends in Phoenix who have to deal with the heat, and see what that computer model says. So we're going to go to Oxnard first. Do we have any clouds? Let's see here. Sky coverage. Here's sky coverage right here. And it does have more than 50% of the sky covered with clouds on Friday morning, Saturday morning. But then after that, it's dry until we get to like next Thursday. Temperatures looks like we'll be in the upper 60s, low 60s there for Friday. And then basically 60s for highs and 50s for lows. And the dew points, what are they going to be? In the 50s. So that tells me there probably will be some low clouds in the morning. That's Oxnard. We looked at the Bakersfield already, getting up into the 90s with no clouds to speak of. Here's the sky coverage for Bakersfield. Nothing but 1%, 3%, a little bit more at the end of the period, but all in all, sunny. Certainly VFR. In San Diego, now we're going to look into the future, and we have a lot more cloud cover there, 57%, 67%, 84% once we get to Tuesday. So temperatures will be much more moderate there, 69, 71, 70 for highs. So very little change. The more cloud cover you bring into an area, it minimizes the extremes. So we see temperatures not changing a whole lot. Lows in the 50s, highs in the upper 60s to near 70 degrees. And dew points, what are they going to be? 50, 50, 50s throughout. Now let's see if it's going to hit 100 degrees in Phoenix. This is PHX. And what do we have? The highs and lows are 90s, 98, 99, 100, 101. So it's going to get pretty hot the middle of next week, probably because upper level high pressure is building in. Sky coverage is negligible, so not much going on there. Okay, we've done that. Now I want to look at the models. I want to actually see the graphics. I want to live. Okay, so we're going to go ahead and take a look at this. And here's the big picture. And see what's going on. Looks like some thunderstorms across the lower Mississippi Valley today. Looks like snow across interior portions of Colorado there. That's the blue that you see. And that's that high pressure system coming down. This is like a little kind of late season push of cool air. Of course, late season pushes of cool air in this part of the world quite often turn out to warm weather for our part of the world. Here you can see the inverted trough. Okay, so if you were to draw a little dashed black line, it would be right along here, Northern California, right off the coast of Oregon. And whenever you see an inverted trough, which means an upside down trough, normally you start with low pressure up here and then the trough goes down to the south. Here, the low pressure is south and the trough goes north. And so that's the inverted part. But anyway, that low pressure system kind of continues, and that's why it's going to get kind of hot. Low pressure moves off the East Coast, and then let's see, now our time is in the upper left-hand corner, so now we're into Monday. No major weather there. Looks like something along the northern Gulf Coast. Now we're into the middle of May. That is Wednesday. That's mid-May. And that's also the beginning of the hurricane season for the Eastern Pacific, not to be confused with the hurricane season for the Atlantic, which begins June 1st. So thunderstorms roll across Dixie there from Louisiana all the way into Georgia. Another push of cold air here looks like moving into the northern high plains. That'll be about Saturday of next week, and it looks like nothing really for us other than possibly some thunderstorm activity in the high Sierra. Now I want to do something rather interesting. We're going to take a look at the satellite shot here. This is from CIRA, and this shows, this is a good look at, let's see, the western United States. So here's the western United States. And you can see a sun glint down here. That is a reflection back from the ocean. Whenever the sun glint is very defined, that means that the water is fairly flat. There's not a whole lot of wave action. If it gets very high waves and high seas, then you don't see it quite as clearly. But what I want to look at here is a neat product, and it is the sea surface temperature. So here's sea surface temperature, which is actually under the clouds. You can see the clouds right there, but you can also see the sea surface temperature under it. So this area here, which is just to the south of Mexico, just to the southwest of Central America, we have some pretty high temperatures of the ocean. And you can see at the bottom, this is the legend. It's in degrees Kelvin. And once we get up to black, and you can see a little bit of black right there, that's 303 and 305 degrees Kelvin, which is 32 degrees Celsius, which is 90 degrees Fahrenheit. So the ocean surface temperature out here is 90 degrees. And if that's the case, I'm thinking, whew, we're probably going to get some tropical activity, especially considering the fact that it's almost tropical storm season anyway. So I'm going to be watching this area down here to see if any tropical storms develop. And you can see the rest of the tropics. Actually, some of the warmest water in the entire Pacific is right here. Also over in the Western Pacific, we see a little bit of black. And of course, black is 90 degrees Fahrenheit, which is, tepid bath water is what that is. And of course, the warmer the temperature, the more light, that's the fuel for thunderstorm activity. Let me look at this real quick here. This is the sea surface temperature anomaly. This is the difference between what it should be and what it is. And I'm just looking at this now. By the way, this has been El Nino, which has been warmer than normal waters in the equatorial Pacific, but now it's shifting. You can see this big stripe of blue right there. That means colder than normal temperature. So we are transitioning from an El Nino to a La Nina. And El Nino means above normal precipitation for the southern half of the country. And La Nina means a dry in the southern half. And that is why I'm forecasting not only a dry summer, hot summer, which is somewhat unrelated to El Nino and all that, but next rain year, I do anticipate it will be a dry. We're not going to have 3 consecutive above normal rain years. That's what I'm saying. Meantime, a lot of above normal water here in the Atlantic, a lot over here in the Pacific. And so I think maybe looking at some tropical storm activity. Okay, so let's go ahead and go way out. We're going to do this and see if we have any tropical storm activity down here with all of that really warm ocean temperature. So here we go. We're going to go into the future. This is the latest model, and let's see, we don't have anything yet. I'm looking down there right where it says pivotal weather, the very bottom. Don't really see anything, but if we go back to the 12Z model run just yesterday, right here, this is yesterday's. So up here, I can pick any of these times as an initialization. So this is yesterday's 12Z model run, and if you look closely at the bottom, right there it is. You can see it. There is a tropical system right there as it's moving out right here. You can kind of see it right down there. This is a tropical storm that would be called Eleta. That is the first tropical storm of the season. And I know that because if we go to the NHC site, and we look at educational resources, some tropical storm names. Here it is, right here, ELETA, Eastern North Pacific storms, right here. If you think it should be Elita, you'll find here that it's actually pronounced Aleta. Okay, so now we know that. I also wanted to look at the Western Pacific, so we can go over here and look at the, we'll just go to Asia here. And this area down here, notice right around the Philippines, this is the Philippines, here's Japan, here's China, here's Southeast Asia, Vietnam. And if we go into the future now, let's see what we have. There's a low that develops right there, and it looks to be a pretty big system. It's this one right down here. This is going to be a typhoon, which gets pretty strong, and it moves right up here to it hits Tokyo. It hits Tokyo, and that'll be on Sunday, the 19th. If in fact that happens. I looked at the model run right before that. We can look at I think 6Z, which was the most recent. The models are run every 6 hours, and I think this run actually took the low and made it even stronger. Right? Yeah, 922. Okay, so a 922 low right here, a 922 millibar low pressure system typhoon. That's pretty strong. 920, by the way, is the cutoff usually between a category 4 and a category 5. So anything below a 920, now we're talking, category 5, super typhoon. But this particular model actually moved it a little bit more to the northwest, I think. Well, maybe not. Okay. So anyway, we'll be looking at that to see what takes place. Okay, and as far as our weather, once again, let us now go to the forecasts. So here they are. So we'll go back several hours and just look and go. And we're going to do TAFs and go. All right. So let's see what we have here. This morning's low in Bakersfield was 11.1, which is 52 degrees, which is exactly what I forecast, by the way. And here is the forecast for Bakersfield. It is the ideal VFR let's go flying forecast. Sky clear, good visibility, variable light winds. Good stuff. All right. How about Oxnard? All right. Just in case Barbara's going to go flying today, it looks like it's going to be pretty good. We got clear skies, generally light winds, well, right down the runway there. 250 at 10. I forget exactly what the runway is, but that's close. And let's see, at 9Z, that's a little after midnight tonight, we go marginal VFR. And this is interesting. We keep it like that until 1630. So here's one of those really good forecasts. They're so confident in their forecast that they actually forecast to the nearest 30 minutes, nearly 24 hours into the future, which is pretty amazing. So, but they don't take it VFR. They only take it to 1700 broken, but I'll bet the next hour probably goes up. The forecast only goes to 18Z. So if it went to 19Z, they'd probably go VFR. Here's San Diego, and looks like they are looking at a little bit of cloudiness earlier, 2400 broken at 17Z, and then it broke out at 1742. We're going to keep it VFR until 3Z, and then we go back with more low clouds. And Phoenix, of course, is going to be fine. Nothing but clear with diurnal winds out of the west during the day, out of the east at night. Okay, so that's pretty much that. Any questions from anybody about the weather, what we have going on? Nobody has any questions. Okay. All right, after that, then we are going to go right into today's topic, which is we're going to kind of wrap up the weather portion of AER 110 DE. So here we go, and we're talking today about a review, and of course, we're not going to forget to take that exam, due on Sunday at midnight-ish. So first, we learned a lot in this, and once you get to the next weather course, advanced aviation weather, we'll dive into much more detail about a lot of things. But anyway, motion and meteors. So we looked at the atmosphere, which is mainly nitrogen, and we do have about 21% oxygen, and that is like the perfect blend. Everything is a blend. It's like the richness of your fuel or lean or whatever. There's a perfect balance there. And so nitrogen is the venue. It's like the cup, and then the active ingredient is all of this oxygen here for all of us animals that really do need oxygen to get into the blood and give us life, basically. And then there's just little bits of traces of carbon dioxide, but there are a lot more plants than there are animals, and they use that in photosynthesis. This is the way the atmosphere is made. There's actually natural helium, believe it or not, in the atmosphere. Not a lot, but a little. Natural neon too. All right, so the atmosphere cools off with height until you get to the tropopause, and that's where all of that cooling with height pauses, and then it turns around and actually goes the other direction, gets warmer with height, and that, of course, is due to ozone in the lower part of the stratosphere, which actually is thermogenic. It creates heat. Then we get up to the stratopause, right around 50 kilometers thereabouts, and then the temperature goes down again until we get to the mesopause, and that's the coldest of all. And then we go into the thermosphere, where temperature goes really, really warm, but it doesn't really matter because there's so few molecules up there. It's not the same thing as being in an oven. There are a couple of very important graphics, and this is one of them. This is the absorption of long wave and short wave radiation, which is electromagnetic energy. It's just radiation from the Earth or from the sun, but you can't see it unless it's visible, and then you can see it. But that's a pretty small part of the big picture here. This is the thermogenic part. So here's, for example, carbon dioxide, 1, 2, 3 little spots here at this wavelength, and this wavelength, which is between 2 and about 13 microns. And a micron, 1 micron is equal to 1 millionth of a meter. So we have a thermogenic carbon dioxide. We also have a lot more thermogenic water vapor is far and away the most impactful thermogenic. Thermogenic means that it simply creates heat. Thermogenic. And this is all long wave on this side. So the waves are getting longer that way. This is short wave going to the left. And you'll notice that we do have a lot of absorption of oxygen and ozone at short waves. And that is ultraviolet light coming in from the sun. And that is the reason the stratosphere actually does not cool off with height like it does in the troposphere, because oxygen and ozone are thermogenic in the stratosphere. We have atmospheric water, of course, and there's plenty of that water vapor. Here's the water vapor molecules. I guess you would expect water vapor, since 70% of the surface of the Earth is water. There's a lot of available water vapor that evaporates from the oceans, and it's just all over the place. It's all over the land, and there's water vapor in the room right now where you are. So there's plenty of water vapor. The water vapor rises in a parcel of air, and then once it changes and condenses to liquid water droplets, then it actually releases a little bit of heat and becomes even more unstable, and rises and rises and rises. So we go from solid to liquid to gas, or gas to liquid to solid. There's that connection right there. And then the all-important latent heat. So this is that kind of secret thing. That's why it's kind of latent. It's there, but you don't. It's there in plain sight, but you don't see it. So vapor becomes liquid whenever we get to the point where the atmosphere can no longer hold the vapor. It's too cold. And there is a direct relationship between the temperature of the atmosphere and its ability to hold water vapor, its ability to keep that water vapor mixed in. At some point, it just doesn't work anymore. And it's a complicated thing, and it has to do with vapor pressure and basically vapor pressure and temperature. So anyway, it condenses, and when it condenses, it releases heat. Heat is released to the atmosphere at the rate of 2,501 joules of energy per gram of water vapor. And so condensation is a warming process. And it's the same thing here going from liquid to solid. Freezing also is in the blue category here, so it releases heat. So even freezing is a warming process, much less energy, 334 joules of energy per gram. But yes, it is counterintuitive that freezing is a warming process. And then we go the other direction, and it is kind of the same thing. And some of those things are somewhat counterintuitive as well. So let's do this. Okay. So if we go from solid to liquid, that is absorption of latent heat from the environment. If you're taking heat from the environment, then that's a cooling process. So melting is a cooling process. Again, counterintuitive. That doesn't make sense, but this does. Evaporation is a cooling process, and that is how our body cools itself in the summer. We have beads of perspiration, and then it evaporates, and we get cooled off at the rate of 2,501 joules of cooling energy per gram of liquid water. Then, of course, we have deposition. This is frost. That is a vapor that goes directly to solid with the most amount of latent heat released to the atmosphere, 2,834 joules per gram. And then sublimation, that is where we go directly from ice to vapor. And that is the biggest cooling process of all. We talked about several different types of clouds. There are 10 genera, that is genus and species. We're not talking species, just the genus. Plural of genus is genera, and there are 10 of them in 4 categories. And here they are. Let's see, we have stratus and stratocumulus and nimbostratus. Those are low clouds. Then we have convective clouds. We have low, we have convective, which is the one that everybody forgets. Everybody has been told by other sources it's low, middle, and high. I'm telling you it is low, middle, high, and convective because it's its own thing. Cumulus and cumulonimbus, those are convective. Then we have middle, that's altocumulus and altostratus. The word alto tells you that it's middle, and that's between 6,500 and 23,000 feet. And then high clouds. And high clouds are up here, cirrus, cirrostratus, and cirrocumulus, and they're all up there. Either they're made of all ice or they're above 6 kilometers or 20,000 feet. Those are the 10 genera of cloud. And clouds, of course, are either liquid or solid. If it's water vapor, you can't see it. So to say that a cloud is a vapor is just technically wrong. There were 100 different kinds of weather, starting with 00 and going to number 99 over here, and we discussed those at length. We discussed the difference between hydrometeors and lithometeors. Let's see. Here's a hydrometeor. That is rain, number 60. Let's see. Here is a lithometeor, smoke. It's number 4. Here's an electrometeor right here, lightning, number 13. And we don't really have any photometeors as a type of present weather, but a halo or a rainbow would be considered a photometeor. So here are all the different types. And the 50s are all drizzle, the 60s are all rain, the 70s are all snow, the 80s are all showers. We did learn about showers. It is a character of precipitation. Character. We have continuous precipitation, intermittent precipitation, and showers. And all showers come from cumulus clouds, upward motion clouds. That makes a shower. And we talked about stability and energy, and of course that interesting density, the vertical density gradient. Gravity is pulling down, but we have some air which is warmer and less dense than the other air all around it. And so if that's the case and gravity is pulling down, then the warmer, less dense air will want to go up. And indeed it does. And so now we have some cumulus clouds there billowing up and are causing some interesting weather, either showers or thunderstorms. Here you can see stable air at the tropopause, and whenever you see that anvil cloud, you think that's as far as as far as they can go vertically. At least the cumulus clouds, they can only go so far. Here's some overshooting tops. It's trying to bubble up into the stratosphere, but the air is stable up there in the stratosphere, and it says, "No, you can't come." So it's like a ceiling, basically, literally a ceiling. So that is because of that interesting dynamic of the ozone layer thermogenic and warming up the stratosphere, so that there's a stable layer up there. It can only go so far. And how do we measure it? How do we do that? Well, we use the skew-T, log P. The skew-T means that the temperature lines are skewed at a 45-degree angle on a skew-T. And the log P means that the pressure reduces not linearly, but logarithmically. And if the temperature is falling really, really fast, like this, then that is very unstable, because you don't have to go too far up, and it's really cold. And so all of this air down here, whether it's warm or not, is relatively warm compared to what's above it, so it'll want to bubble up. Stable air over here means that the air is cooling off at a very, very slow rate, or even getting warmer with height. It might be an inversion where it warms up with height. And then most of the time we're conditionally unstable, meaning it all depends on the case-by-case situation, if there is a front or a mountain range or the sun is coming up or something like that. We did talk briefly about the ideal gas law, and that's what this is. This tells us that pressure and volume are equal basically to temperature. If pressure goes up, that means volume goes down. If volume goes up, that means pressure goes down. And there's a relationship here with temperature. This is the universal gas constant. This is Avogadro's constant right there. So pressure, volume, and temperature are all related. It also says, by the same thing here, that there is no heat gained or lost in an adiabatic process. Adiabatic, diabatic, just diabatic right there means that heat is added. You start a fire, you have shortwave energy come in, but adiabatic right there means there is no heat. And so it's all a function of pressure and volume changes. And you probably all know that. The work is done, but the adiabatic process shows that as the pressure increases, the temperature increases. So here we are, pressure is going up and the temperature is going up. So this is interesting here. That's the adiabatic process. We have dry adiabats and moist adiabats. And because of the latent heat of condensation, which releases heat as soon as water vapor changes its molecular and chemical structure to be a little bit more structured, basically, to be a little bit more in line. It actually becomes visible. It's not as chaotic as water vapor. Once that happens, then it mitigates the lapse rate. So rather than cooling off at the normal dry adiabatic lapse rate of 5.6 Fahrenheit degrees per 1,000 feet, instead it's more like 3.4 Fahrenheit degrees per 1,000 feet. And so that's the difference between the two adiabats. And an adiabat is a lapse rate, how fast the temperature is changing with height. We have determined that unstable air in the atmosphere, which means really cold air above hot air. You know, it's normally cooler with height, but I mean, if you just extend that to an extreme, then we'll get an increase in turbulence, an increase in convection, and a decrease in predictability. Because with showers, they just sort of pop up wherever. There is a difference between showery precipitation, which is hard to predict precisely where the shower will be, compared to a shield of rain coming in with a low pressure system where it's raining everywhere. And the probability of precipitation is very high. With showers, the probability of precipitation will generally be lower, 20%, something like that, because the probability of precipitation is equal to the confidence times the area. And if you have a big area here and there's going to be showers just all over the place here, you can't be sure which specific spot is going to have precipitation. That's why in the summertime, 20 and 30 and maybe 40% probability is much more likely than in the wintertime when we have 80 and 90 and 100% probability, because we're not talking showers in the summertime, in the wintertime rather. We're talking showers in the summertime. So we talked about synoptic weather, and here we are. We're looking at lows and highs and fronts and weather station symbols and temperatures and all that stuff. Everything that you can plot on a weather map. How important is that? It all starts with highs and lows, and so there's differential heating. So all of the solar radiation comes in. It warms some places more than others. Wherever it gets warmer, the air rises, and we get a low pressure system because the air just went up, so there's no more air left. And so high pressure will then fill in, and that is the origin of wind. Wind is caused by differential heating. This was an important thing right here. We talked about the general circulation of the general wind circulation of the world. And this is kind of the big picture, but it's happening. So here at the equator, 0 degrees, we have the sun coming down with most of its energy most of the year. We're just going to look at the northern hemisphere over here, not the southern hemisphere, because it's just a mirror image. So we have the Hadley cell due to the strong updraft that reaches the tropical tropopause, which may be 60,000 feet, very high. It's higher. The tropopause gets higher and higher the farther south you get, lower and lower the farther north you get. Some things are pretty simple, just like that. The Hadley cell comes all the way up here to about 30 degrees north latitude, and then we get all this downward motion, and high pressure builds up here because of all the massive molecules coming down from above. So we get a big high, a subtropical high right there. You can see it at 30 degrees north. That's the Hadley cell. And then some of that goes back to the south. Some of the wind goes to the north. The wind is, well, it's sinking air here. It can't go into the ground, so it has to go north and south. And so it goes to the north here, and this becomes the Ferrel cell. And the Ferrel cell goes about as far north as the Hadley cell went, which is 30 degrees. It goes from 0 to 30 and now up to 60 degrees. Nice numbers to remember there. And we get this upward motion, and this is the polar front right here. So we get semi-permanent low pressure systems right around 60 degrees north. And again, very important, remember this, low pressure is at 60 degrees north, not because it's so hot there, not because it's a tropical jungle and all of the hot air rises because it's so less dense. That all happens over here at the equator. These are just simply cogs in a machine, that's all. So we have the Hadley cell, the Ferrel cell, and then the polar cell. And so of course we have upward motion. Some goes back south, some goes to the north. A very low polar tropopause, maybe 20,000 feet, very low. And then finally the winds sink at the poles. So we have high pressure there. So low pressure at the equator, high pressure at 30 degrees north, low pressure at 60, and high pressure at 90. It's just that simple. Then we get the winds, which are curved by the Coriolis effect to the right in the northern hemisphere. And so we get northeasterly trade winds across this area here, generally south of 30 degrees north. And then north of 30 degrees north up to about 60 degrees, we have the westerlies. And that is the general circulation. And within the mid latitudes, that would be the westerlies, we have synoptic features. We have warm fronts, cold fronts, occluded fronts, highs and lows, and things like that. By the way, these synoptic features do not exist in the tropics. We don't have it down there because the air mass is all pretty much homogeneous. It's the same basic hot and humid air mass. But we do have fronts and big changes in the mid latitudes. And of course, here they are. There are 4 different kinds of fronts, and here they are. Cold front, which is blue with saw teeth, the warm front, which is red with half moons or semicircles. We have a stationary front, which is a boundary that doesn't move, and the occluded front, which is a situation where all of the warm air around an extratropical low pressure system moves up off the ground. Occluded fronts are more about the low pressure system than anything else. You can have frontogenesis, that is where a boundary is developing along between 2 air masses, and one is moving and kind of invading the other. And this is what that looks like. You can have frontalysis, which is a washing out or mixing of the 2 air masses, so there is no boundary anymore. That usually happens. You cannot have occluded frontogenesis because, again, it's all about the low pressure system and the development of the low, the strength of the low, the maturity of the low. But you can have occluded frontalis, where the whole thing pretty much washes out. We have, these are all extratropical, and then down to the lower right, we have tropical systems. And tropical systems, again, there are basically 2 types of air masses, warm core and cold core. Warm core are called tropical. They are warmer. Here's the isotherms. You can see that it's warmer in the middle. And then we have 2 versions of that. We have the high above a high, which is like the Bermuda high or perhaps the North Pacific high. It's just high pressure everywhere. Or we have the tropical cyclone, which is a low pressure system, a very deep low pressure system, like the one which is going to be developing in the Western Pacific. It'll be a typhoon. It's going to hit Japan probably. It'll be a big, deep, low pressure system with rain bands and extremely low pressure, but aloft is going to be a high. It's going to be a high with winds that are blowing clockwise, like a high pressure system. And that'll provide the vertical ventilation for that system. Extratropical lows come in 2 versions as well. We can have this, which is a low pressure system aloft and a high pressure system at the ground. And it is a cold core, meaning that the middle of the system is colder than the sides. Or we can just have a semi-permanent low pressure system at 60 degrees north, right at the top of the Ferrel cell there. And it's a low over a low, and that's your other typical thing. So we got 4 different iterations of 2 different basic atmospheres: warm core tropical and cold core extratropical, meaning that it's not tropical, not that it's more tropical, which is just kind of a weird thing. Why do they call it that? So we've got jet streams, and jet streams are dividing very cold, low pressure to the north from very warm, high pressure to the south, just a river of wind. And of course, we did talk about Coriolis, and this was interesting. A lot of people had some views on this. Question is Coriolis a force? Is it a force? And I wanted to hear what people had to say about that. We have high pressure over here, low pressure over here. We'll always have the pressure gradient force always pulling in toward low pressure. And that's just the second law of thermodynamics. Everything flows downhill, goes from hot to cold, high to low. It always goes that way. That's just nature. And so the winds blow that direction. But because of Coriolis, which is always moving 90 degrees to the right in the northern hemisphere, we finally get this balance down here between the pressure gradient force, which is always pulling toward low pressure, and the Coriolis force, which is always pulling to the right. So the motion goes just right along the lines here. There's a thing called Buy-Ballott's law. Buy, like that, that's B-U-Y, Buy-Ballott's law. And that is basically, that's a law. And that's basically whenever the wind is blowing at your back, the low pressure system is always to the left. It's just that simple, Buy-Ballott's law. And that is basically what we have right here. Then we talked about some interesting disasters, I guess. I guess all disasters are certainly interesting to some degree. And there were 7 of them that were major fatal weather-related mishaps. The big one was 583 fatalities in Tenerife and Canary Islands. It was due to thick fog, 2 huge 747 aircraft that were all fully loaded. KLM and Pan Am, there was a problem with situational awareness, and because of that, nearly 600 people were dead. There were other mitigating circumstances too. There was no ADS-B. Nobody knew where anybody was. People were not, the KLM, they did not really know what was going on, but they moved forward anyway. So that was a big problem. In the fog in 1977, there was another big fatality, the group of fatalities here from a Ilyushin 76. This was the Iranian Revolutionary Guard trying to come into Kerman. They had a problem with turbulence, snow, probably icing, and they crashed into a mountain peak a little bit short of the runway, like 19 nautical miles. Speaking of icing in winter, 256 fatalities from an aircraft that was flying from Cairo to Fort Campbell with a stopover in Gander, Newfoundland. Ice contamination leading edge, the upper surface of the wings. They did not do any de-icing in Newfoundland there, and because of that, they took off and immediately crashed, not even a mile after the end of the runway. Speaking of icing, another big thing, we talked about icing last time too. Here's that Air France Flight 447, which was a severe icing situation in a tropical thunderstorm over 30,000 feet in the tropical Atlantic, 228 deaths. Here was the amazing story of Julianne Koepke, who, and I hope you will never forget this. This woman, when she was 18 years old, had just graduated from high school, was outside the aircraft at 22,000 feet, falling without a parachute, somehow landed and survived, and then took her about 11 days after that to finally get to safety. And she lived to tell about it. They flew into a thunderstorm. That was the problem there with that particular aircraft. Speaking of thunderstorms, here is the famous Delta Flight 191. This is the flight that was downed by a microburst from a thunderstorm. They were trying to land in Dallas, and then they just had a strong microburst behind them. They stalled, and and 137 people were killed. Not everybody, but most of the flight was. But because of this, the silver lining is that the terminal Doppler weather radar system was developed in the 1980s, and that is a high resolution system that can tell you where wind shear is. And so that has probably saved a lot of lives, now that I think about it. More fog related problems in Detroit. This was back in 1990. Again, situational disorientation, positional uncertainty, thick fog, big problem. Always know where you're at. And then finally, was it weather related? Yeah, probably. This was Learjet 35 Alpha, and it crashed in the San Diego area back in just a few years ago. And the weather wasn't all that bad. It was, we talked about that. We talked also about the weather models. We have the art of weather, and then that becomes the science of weather. We have moved boldly into the future, from Farmer John up to IBM and Apple and all of that, and how important physics and mathematics is in engineering, but also in weather. The scientific method is to question something that you see, observe it extensively, do observations, research, develop a hypothesis, test the hypothesis. Maybe the hardest part is coming up with a hypothesis. You have to figure out, well, it must be this, and then test it and see if it really is, and then make a conclusion. And then after you do that, do it again for whatever the next thing is. That is the scientific method. And that is one of the reasons, because the scientific method has been invoked, that we have computer models that really do pretty well. We've gone through the conceptual phase, which is the early 1900s, when Bjerknes wrote down the 7 primitive equations, a Norwegian guy, in 1904. And then the practical era, which was when we actually had computers that were actually making forecasts in the 1950s. Reliable in the 1990s. Many of you were born in the 1990s. And that's when it became reliable. And then just default about 5 years ago, where that is now the way that forecasts are issued. If you go to any National Weather Service forecast, and there it is, you can see, sunny this afternoon, a chance for rain tomorrow, whatever. That comes not from a person, but from a computer. The National Blend of Models. The National Blend of Models, the primary forecast of weather parameters. Meteorologists only make changes if the predictions are really, really obviously wrong. And that can happen, by the way. If you have some bad data going into a computer model, then the forecast will be just as bad and get worse with time too. So model output statistics, MOS, that is something that you can compare on your ForeFlight apps to know what the weather is like. And you should always do that. Now, around California, the weather is pretty predictable, especially the Bakersfield area in the summertime. There's not much cloud cover or anything. But there are clouds in Southern California, and there are IMC conditions and all that. And if there ever are significant weather issues, you should always be sure of what the weather is going to be, because you're flying through it. You are ultimately responsible. And model output statistics helps you with that. Then we looked at thunderstorms and hazards, and we came up with the cookbook here. And these are the 5 things. And everybody says, well, there's these 3, but I've never heard of these before. Well, that's just as important, because you can have these 3 things all in place, but without a trigger, nothing's going to happen. It'll just be latent, sort of like latent heat. It'll just be there. If water vapor doesn't condense into liquid water to make clouds, then there won't be any latent heat released, even though it could be. So these are we'll call these the latent ingredients that you have to have. But then you got to have a trigger, and then it happens, and then it's not going to continue unless you maintain it. So there are 5 parts to the thunderstorm recipe. And of course, there are many other elements to look at. In this case, we're looking at synoptic weather features and their positions, and fronts, jets, low-level jets, polar jets, and we come up with the perfect location for the bad weather right there. So we look at all those things. And of course, the Storm Prediction Center, they are your go-to location for everything that you need to know regarding severe weather, thunderstorms, and more actually. Fire weather is a big thing with SPC. And you can always look at any of their mesoscale analyses to see how bad the weather is or how good the weather is wherever you're planning on going. And of course, convective SIGMETs are issued, and that tells you exactly where the storms are, how tall they are, where they're going, how long they're going to be there. and things that you need to know if you find a thunderstorm or cumulonimbus in your path or in your proposed path. Of course, also there's ATC, which will vector you around these things. But you don't want to get within, what is it, 25 miles of a thunderstorm. We talked general weather hazards, turbulence, which is probably the most impacted. Well, maybe that's not the word. There's more turbulence that you will deal with than anything else. You will deal with turbulence more likely than thunderstorms because you know to stay away from thunderstorms, and icing is just not as prevalent usually as turbulence. Turbulence is like ubiquitous, it's everywhere. So you'll be dealing with turbulence, and we determined that turbulence is simply caused by conflicting vectors. So, and that causes chaos in the flow, and chaos for you if your vector is in conflict with the vector of the atmosphere. And quite often we have different vectors of wind in the atmosphere itself, and that's what causes different types of turbulence. Convective turbulence, of course, is the upward air parcels that bump up against you. Mechanical turbulence is a turbulence that is caused by things that are vertical and they impinge upon the laminar flow, and then we get chaos over here. This is all because of Newton's third law. Newton's third, and that is the one that says there is an equal and opposite reaction when two different particles collide, basically. Newton was right about that, and that is why we have mechanical turbulence. Orographic turbulence, of course, is a type of mechanical turbulence. It is simply something very vertical sticking out of the otherwise smooth ground, and it causes things like lenticular clouds and all these. Here's a cap cloud right here, and these clouds are very, very turbulence. So you want to always stay clear. You see something like the mothership right here, you want to stay away from that because it will tear you up. Clear air turbulence is due to synoptic features in the usually upper atmosphere, jet streams and things like that, where there are very different flows of air in very close proximity, and usually very tight horizontal thermal gradients that will cause clear air turbulence, which can be very bad. And then wake turbulence, of course, is just stay clear of the air right behind a large aircraft, or any aircraft for that matter. I mean, your Cessna 172 creates wake turbulence too. That may affect birds and things like that. No, just kidding. But yeah, it's a real deal. And wake turbulence does happen at altitude. If you are caught in a microburst at low altitude, fly 90 degrees to the outflow until you are clear of danger. That is good words for the wise if you find yourself in that situation. Finally, we talked about icing. That was the last thing we talked about. Icing is can be very, very impactful. We have structural icing, which is icing that forms like barnacles basically on your aircraft, and it changes the shape of your wing, which is the last thing you want to do, and adds weight and drag and all that. And then there's induction icing, which is talking about carburetors that can form ice, and it's like cholesterol in the bloodstream, and it'll cut off fuel to your engine, and that's a problem if you want your engine to work. And there's also instrumentation icing, which is basically a type of structural icing where your pitot tube gets iced up and then you don't know how fast you're going. So the big thing to remember here is the minus 24, that is the halfway point. Anything colder than minus 24 for your outside air temperature, the probability of icing begins to really go down. Anything warmer than minus 24, it goes up until you get to about freezing. We have rime icing, which is formed in stratiform clouds caused by tiny air bubbles. It's white. We have clear icing, which is caused by cumuliform clouds or freezing rain, and it is thick and glazy. And then mixed icing is a little bit of both. And there are all sorts of resources on aviationweather.gov that can help you with not only turbulence and icing SIGMETs and airmets, but also information on the probability of icing or the probability of turbulence and all that. And that is it. We have learned an awful lot. In some cases, I think we've learned things we didn't know before. And so the only thing that's left, other than finishing whatever assignments need to be done, is take the 30-question exam. Make sure you take it. It's open book, and it is due on Sunday at 11:59. Let's go ahead and give it this. Okay, so are there any questions that anybody has about anything? Okay, so we have Austin.
I think so. The only thing I can think of, Miles, is that somebody had raised a question about the assignment for week 10. And I think I'll just have to go in and clarify. I cannot find it. So
did you say for week 10?
Week 10. You know, our cross country.
Oh, yeah, that. Okay, all right. And so it's not specifically weather related.
No, not weather related. It had to do with distances. But I'm assuming you're going to help grade that one. Or can you?
Yeah, sure. I'll be happy to once again. My pleasure. And with the next AER 110, we're not going to be late like we were this time. Blame it on the moon. It was the eclipse that did it.
I think we're back on our normal schedule for the next AER 110. And I need to touch base with you. You can take this off the recording. I have
okay, let's do that right now. So good luck to everybody, and see you next time.